Hello everyone, my name is Parveen. Today I'm gonna present our paper that's been accepted in ICASSP 2023. The title of our paper is A Unified Uncertainty-Aware Exploration Combining Epistemic and Aleatory Uncertainty. I'm gonna start the presentation by providing a high-level summary of our work, then we dive into the more detail. Specifically, we focus on uncertainty-aware exploration in the reinforcement learning. There are two types of uncertainty generally considered in the RL literature, namely epistemic uncertainty and aleatory uncertainty. Epistemic uncertainty refers to the agent's uncertainty about the environment, and more sample received from the environment, its value would be less. On the other hand, aleatory uncertainty arises from the intrinsic stochastic events within the environment, and its value is irreducible. It's been shown that by considering these two uncertainties for action selection, we can improve sample efficiency and risk sensitivity of our agents. There are some work in the literature that estimated each uncertainty independently and then consider an additive formulation of those two for action selection. However, in this work, we tried to derive a theoretical connection between these two uncertainties, and based on this connection, we could propose an algorithm that simultaneously estimated both uncertainty for action selection. The experimental results show that our algorithm outperforms the other methods in terms of sample efficiency and stability to the environment changes. Our method is built on the distributional reinforcement learning. So first, let's get some background information about it. Similar to the classical reinforcement learning, distributional reinforcement learning models the agent's environment interaction as a Markov decision process. Specifically, at a time step t, the environment is at some state that agent has access to. And based on this state, the agent chooses and performs an action. And as a result of performing that action, the environment will transit to the next state and gives a reward value as a feedback to the agent. The strategy that agent uses in order to choose its action is called policy and is denoted with the letter pi. The objective in the distributional RL is to learn the distribution of the returns that's denoted with the capital Z is a random variable that's defined as the summation of the future rewards that agents receive from the environment. Distributional RL learns the return distribution by approximating it with a neural network with the parameters of theta and then define a loss function based on the so-called distributional Bellman equation. Once we learn the return distribution, we can capture the aleatory uncertainty. However, since the environment model is unknown, so agent cannot be completely reliable to these parameters. In other words, the agent has some kind of epistemic uncertainty about these parameters of theta, and these parameters aren't deterministic anymore. Now the question is that, okay, how can we incorporate the epistemic uncertainty about theta in the distributional RL? In order to answer this question, we propose our algorithm. First of all, we presented the epistemic uncertainty about theta in a form of belief distribution of a random variable capital theta, taking value on the small theta. Then we model this belief distribution as a mixture of k-direct delta function with the parameters of phi that's showing the location and the weight of each delta function. Therefore, our distributional Bellman equation would be converted to a belief-based distributional Bellman equation such that instead of having these parameters theta, we do have a continuous probability distribution over the values of theta. However, we know that fitting continuous probability distribution as a parameters of a neural network is impossible. In order to tackle this issue, we try to summarize this return distribution into a feature vector. In order to do that, first of all, we calculated the moment generating function of the random variable of theta. We know that moment generating function of a random variable is alternative specification of that random variable. Once we found its moment generating function, we derive its moment of the random variable and puts all of those moments in a feature vector m tilde beside each other. Therefore, we summarize our return distribution with the feature vector of m tilde, and our belief-based distributional Bellman equation would be converted to this equation with the parameters of m tilde. Now we can learn these 5 parameters by minimizing the JTD loss function between two sides of this equation. Once we learned this distribution, we found out that its expected value in fact captured the epistemic uncertainty, while its variance indeed captures the aleatory uncertainty. The agent should try to be optimistic with respect to epistemic uncertainty and try to maximize its information about this uncertainty. However, it should avoid the areas with high aleatory uncertainty because that's irreducible and are risky areas. And finally, in order to evaluate our algorithm, we performed that on 3 tasks, including 2 Atari games and 1 autonomous vehicle driving simulator. And we compared the result with 3 algorithms that consider either the epistemic uncertainty, aleatory uncertainty, or an additive formulation of both. We measured the results in terms of the cumulative rewards received from the environment, and results showed that our algorithm outperformed the 3 other methods. And here is the end of my presentation. Thank you for listening.